The new stuff that we're going to be talking about are acids and bases. And I'm going to start off by defining what an acid and a base is. There happen to be two ways that acids and bases are defined. The first one is the Arrhenius acid and base. This is the original one. And what Arrhenius said is that an acid is something that produces a hydrogen ion in an aqueous solution. So, meaning when it goes into water, it dissolves and produces an H plus ion. That H plus ion can also be written as an H3O plus ion. And when it's written as an H3O plus ion, it's called a hydronium ion. But for you guys, these are the same. Okay? And so it's kind of confusing, but they'll be interchangeable. So an example of a Arrhenius acid would be hydrogen chloride. HCl is a gas. When it gets thrown into water, it breaks up into a hydrogen ion plus a chloride ion. And these are aqueous. Alright, so that is what an acid is going to do in solution. It has to be in water to be an acid. Now, from what we've talked about earlier on, normally acids will have the hydrogen placed in front of the formula, so it's kind of a heads up that that is indeed an acid. And the point being that when it mixes with water, you end up with that critter right there, and that makes it an acid. All right, so now I'm going to talk about an Arrhenius base. So an Arrhenius base simply is something that produces a hydroxide ion. Not sure why there's an X there. Hydroxide ion in solution. And remembering back, hopefully you remember that a hydroxide ion is an OH minus ion. So if I take something like sodium hydroxide, which we've used a ton of in this class, all right, sodium hydroxide, it's an Arrhenius base. When it goes into solution, I get a sodium ion that is now dissolved aqueous plus a hydroxide ion, which is aqueous, and this is the solid, and because it produces that hydronium ion, it would be considered a base. And so bases, Arrhenius bases, are always going to have that OH tagged onto them. Now, this is kind of a little sideline on acids and bases, but if you take an acid and you add it to a base, you will neutralize the acid with the base, and you will form a salt and water. This is kind of what keeps the world from, getting totally messed up with acids and bases, because they neutralize each other out. So with the example that I just gave, here's HCl plus NaOH, the base. The salt that's going to come out of that is sodium chloride and water, H2O. So this is neutralization. All right. And that's kind of what keeps things going. Now, I got another definition of an acid and base, which is a little more complicated. And this acid and base is called a Bronsted-Lowry definition. And it's more complicated, just flat out is. A Bronsted-Lowry will always include water. Water as a reactant. And as it turns out, it's in a Bronsted-Lowry acid or base, it's the fact that that acid or that base turns water into the acid or base. So it's going to work like this. Okay, I'll take this acid, C2H3O2. This is acetic acid, so it's what's in vinegar. And again, it's got the hydrogen in the front, you know, so it kind of gives you a clue that maybe it's an acid, and it is an acid. All right, so I'm going to take this acetic acid, and I'm going to react it with water. So H2O is always in a Bronsted-Lowry acid-base reaction. The other thing about Bronsted-Lowry acid-base reactions is these are always in equilibrium. So there's always a double arrow going back and forth. And what's going to happen now is this hydrogen is going to go and launch onto the water, or the water is going to pull the hydrogen off, producing H3O+, which from the Arrhenius was a definition of an acid as well, leaving behind the C2H3O2- ion. So what you have here is the fact that when acetic acid gets thrown into water, it gives up a hydrogen to the water, producing the hydronium ion right here, which is going to be acidic. Okay? And these things always happen in what are called conjugate pairs. And I can link these. Okay? I can link them this way, and I can link these two guys this way. And Bronsted-Lowry acids, their definition, I better hurry up on this, is an acid is a proton donor. And that's exactly what happened, because a proton is really nothing more than an H3O+. Well, it's the hydrogen. Hydrogen ion right here, without an electron, is a proton. And so this conjugate pair right here, this would be labeled as the acid. That then makes, and this is where it's easier than it looks, makes H2O act as a base, because I'll give you the definition of a base in a second, producing H3O+, which is an acid, and C2H3O2, because it's a reversible reaction, becomes the base. Boy, we'll need some work on this, but that's how it works. So these are always conjugate pairs. The acid right here goes to form the base over there, and the base on the reactant side goes to form the acid right there. Okay? So, in the minute and a half I got left, I guess, a base, according to Bronsted-Lowry, is a proton, proton acceptor. And here's how this works. Okay, here's a definition of here's an example. I'm going to use ammonia. Okay, if you looked at ammonia, you wouldn't realize that it's a base, but it is a base because it does what all Bronsted-Lowry acids and bases do. It turns water into the acid or the base. Well, in this case, it's going to turn water into a base. How's it going to do that? It's going to steal a hydrogen off of the water, producing NH4+, leaving behind a hydroxide. So the end result is the same as an Arrhenius. You're always ending up with an acid or base as a product side, but in this case it's an equilibrium and it's going to work like that. I again have conjugate pairs. Arrhenius says that the base is going to accept a proton, and it did right here, making this the acid. That means water was the acid, forming the base right there. Okay?